We wanted to build something we'd never built before. Something that would challenge us, something we'd learn from, something we'd enjoy.
Momentum was a challenge for all of that to take off.
Momentum was
Introduction to thinking outside the box.
A great way to practice time management.
the perfect opportunity to become a better leader. A good way to practice
Arduino design.
presentation.
Control
I'm a freshman in course 6-2, that's electrical engineering and computer science. And at the start of Momentum, all I could really do was build a bridge out of basswood.
I'm Eric Reel. I'm a freshman. I'll be doing course 16, which is aerospace engineering. And the first week of IIP, I learned how to make an LED blink using Arduino.
I'm David Wu. I'm a freshman also, and I will be studying mechanical engineering and computer science. The first week of IIP was the first time I ever flew a quadcopter.
I'm Motio Gunshina. I'm a freshman class of 2017. I will be majoring in mechanical engineering course 2. And prior to Momentum, I had no experience whatsoever with programming or Arduino.
And my name is Brianna Barrios. I'm planning to be course 6-7, computer science and molecular biology. And before IAP, I had never built anything of this scale, ever.
And together, we are
Acceleronix.
We've been around for quite some time, actually. Just about since the 10th of January. Brings our lifespan to up to 30 years if my calendar is correct. We started off as just modestly named Team 3. We had a vision. I'm here to talk about it.
So yeah, before diving straight into the challenge, we decided to take a step back and find out really, as a team, what our purpose was in Momentum, what we wanted to get out of Momentum. So what's quite nice is that we were pretty much on the same page the whole way through in terms of we were definitely sure we wanted to take risks, we wanted to take on a challenge, and we wanted to learn. And we put that a little bit over the actual competition in and of itself.
And speaking of competition, there's our challenge. And our challenge is divided into two. So our first challenge was what you saw in the video Danielle produced, was flying through a pentagonal path, so 5 hoops positioned at different heights. Again, flying through them in order, so making up that pentagon, and doing it in under 10 minutes, and optimally hitting the least number, if not at all, of the hoops in the process. Our second challenge is a bit more intricate in that it involved actual image sensing, so I should say chemical sensing. So we're having 4 stations. The positions of them are unknown, but they're spaced out in this kind of layout. 2 of the stations will just be there for us to take pictures of. And another 2 are going to be surrounded by balloons. Now our task is to approach those balloons with a sharp object placed at our phantom, dip onto them, pop the balloons, and then using the chemical resistor that we've installed onto our phantom actually detect live, in our case, what chemical was present at those 2 stations. There's also a danger zone, which you'll notice indicated over here. Now its position we really were aware of until the day of the competition. So our task was also, as we were flying through the stations, to avoid the danger zone and complete it all ideally in under 5 minutes.
So now for the basic design of our quadcopter. So we decided on 3 different routes that we could possibly take to achieve the goal we set out to do. So we could either go with direct feed with line of sight, which would be the easiest way to go, or we could go with direct feed, direct control with GoPro video feed with no line of sight. So these 2 routes had both its advantages. So for the direct control with line of sight, it was definitely the easiest to go through, and it had the highest expectancy of success. So no matter what, we knew that out of the 3 routes we would take, direct control with line of sight would definitely give us the highest expectancy of success. And then for direct control with the GoPro video feed and no line of sight, we had a point multiplier of about 5, which was way more than the point multiplier for direct control with line of sight. It was also quite feasible to do. And although we would have delayed video feed with enough practice, we would be able to accomplish that route. Prior to momentum, we all decided that we want to get the best out of momentum and challenge ourselves as much as possible, and most of all, learn a lot as well. So we decided to go with full autonomy.
Going with full autonomy, we knew that there were probably going to be a lot of challenges and a lot of risks to take. But before we even dove into how we were going to make it autonomous, we came up with a plan B. So we assigned one of our team members, Monty, to become very knowledgeable with how to fly the quadcopter and would know how to orient it well, would know how to drive it well, would know what speed to drive at. And once we decided that, we actually decided how we were going to go autonomous. So to become autonomous, we had to command the quadcopter using the remote control. We had to position it. We had to figure out positioning, like how it was, where it was supposed to go. We needed lots and lots of time to figure out what technology we were going to use and what sensors we were going to put on our copter. And we also needed to push our skill sets to new heights. Before this competition, a lot of us were familiar with the technology, but we're not very knowledgeable about it. And this becoming autonomous, we would have to push our skills to new heights.
So the first problem we tackled in implementing autonomy was how do we actually send commands to the quadcopter? We quickly learned that we had no way to hack into the Phantom microcontroller. It wasn't accessible to us at all, so we considered manipulating the actual remote. So our original idea was to open up the remote and mess with the internal circuitry, but then we considered that that would run the risk of damaging the remote and leaving us with a non-functional quadcopter for the actual competition. So instead we decided to make a mount of servos to manipulate the joysticks and have it control the quadcopter based on that. In order to test the feasibility of having the remote control, we wanted to test how stable it was during flight. And we took it out to Killian Court and flew it.
I mean, this is wild. How stable it is.
Yeah, so outdoors with GPS positioning, it was very stable, and we believed that we could make it work autonomously based off of that.
So to go through the whole autonomy thing, making the remote control the quadcopter pretty well, we decided to go through wireless transmittings between two Arduinos. Arduino Uno would be on the actual quadcopter, and the Arduino Mega would be on the controller. On the controller, we would also, on the quadcopter, we would have the ultrasonic rangefinder to measure height. We would have a digital compass to figure out orientation. We would have a transmitter that would send all this information back to the other Arduino. We would have the chemical resistor to identify what chemicals were at each station. We would have a needle to pop the balloon, and we would have a GoPro for image, to just have an image feed. And on the actual controller, we would have full rotation servos to control the joysticks, and we'd have the receiver to actually receive the data that's coming from the quadcopter.
So we had the ultrasonic giving us our position relative to the ground, or height, and we had a digital compass to give us the orientation. But what we lacked was the actual position relative to the origin, unfortunately. This was a pretty big problem for us. We considered a ton of options. On a larger scale, people can use GPS to determine where the quadcopter is. But with what we had on a small scale, it's a big problem that many people have tried to tackle. UPenn spends thousands and thousands of dollars on a whole camera setup around the room to get 3D positioning accurate to fly quadcopters indoors. Fortunately, we don't have that amount of money. So we considered using laser rangefinders to bounce off walls and give us the position relative to the wall, using RF transmitters and calculating the time it took for the transmission to be received, and then triangulating the position based off of that. We threw these ideas away because of budget and the time it would take to implement and the feasibility. We considered dead reckoning a little bit and sort of pursued it, but This was a really big problem with implementing autonomous, so we tried to use one of our greatest resources, the TAs, and went to talk to Hunter, who gave us the idea of using a camera mounted above the field to give us a view, and image processing to locate the quadcopter. So here we use MATLAB to, well, not MATLAB. We use MATLAB to isolate the phantom based off of the brightness of the color and the size of it. And we can take that, the pixel coordinates of it, and translate it in combination with the height to get the location relative to the origin. Here's just an example of us processing out everything except for the quadcopter.
So our budget, well, yeah, it's about time to talk about money. So in terms of optimizing money we were given by the OME, which amounted to $100, I'd say we did pretty well with just $1 shy of it. So we purchased an ultrasonic rangefinder, 4 full rotation servos, as you will see soon, a digital compass for orientation control, and then the transmitter and the receiver, as you've certainly heard quite a bit about. Now, there are also external costs associated with what we've been doing for Momentum, and this would not have been possible without our sponsors and without the OME. So thank you. You'll get to hear that again from us. So the Arduino Uno was paid for, the Phantom quadcopter, which amounted to a staggering $500, a GoPro, surprisingly expensive, carbon nanotube pallets, and then all the materials we wound up using at D-Lab and all the places that we ended up working and assembling our final product.
So after testing it outdoors, we actually flew it indoors because it was too cold to just fly again. And we realized that it was inherently unstable and drifted like crazy indoors. And so it turns out GPS is awesome. So we, at this point, completely threw out the option of dead reckoning because that was just absolutely crazy, the amount of drift, as if you saw in the video how much it was wobbling. It was like that many corrections for the flight. So
We also have a picture of this.
So yeah, we also attempted to fly, at least have a takeoff and landing sequence that's autonomous. And as you can see, it's a little bit tricky and dangerous. You'll see in the next video, we got a little bit smarter and put weights on it. We're still having trouble with implementing autonomous flight. So we actually ended up using Mr. Plan B.
So here's a new acronym. It's not an MIT acronym, but you might want to consider it our savior here. TGFPB. It's not a class name or anything. Thank goodness for Plan B. There's no for Plan B. Well, there it was.
Okay, so I was Plan B. So for the final product, we decided to go with direct control with line of sight, so I was the pilot for the whole course. So for the final product, we still implemented some electrical components onto our quadcopter and onto the controller. Onto the quadcopter, we had the RF transmitter, the GoPro camera resistor, needle, and the ultrasonic rangefinder. We also needed the rangefinder to help us give us the height off the ground when going through the loops, which helped a lot when piloting the quadcopter to the course. Although the needle didn't work because the balloons were quite weird, I don't know, but we were still able to test the camera resistor after the competition.
So there was also the matter of how we were going to mount all these instruments onto our GoPro, onto our Phantom, I should say. Now, the first approach slightly resembles a sandwich, and we quickly came to realize that that was not the smart idea. So
We came
went
up
back,
with a new design.
and this is what we came up with.
The design, this new design was attached more with Velcro so that if anything became disconnected, we could easily take it off and reconnect it. It was also much more accessible from the outside. So in case anything malfunctioned, we can just fix it straight from the outside. But we also gave enough space for the sensors. The ultrasonic rangefinder is right behind it, and so is the camera resistor, so it can have enough space to detect.
Furthermore, we also took advantage of the fact that the screws we found actually fit snugly into the into the Phantom, and we used that to stabilize the platform that would actually keep the rangefinder level.
So what did we actually accomplish? We got the RF transmitter and receiver functional. It only cost us $8, and we got real-time data coming from the Arduino on board the Phantom. And we had the camera resistor functional. We could identify if it was index, or Acceleronix. And we had continuous ultrasonic feedback, which helped us with the first challenge, flying through hoops. We knew what height we were at the whole time. We were also able to finish the mount for the remote, so we had the servos moving the joysticks.
And as with anything, it's nice to know that we can do more than just fly over hoops and detect Clorox. So here are the applications of what we've been building, actually. So as we were doing this, we put a fair amount of thought into what it would do for us in the real world. So imagine now you've got some kind of emission source, industrial, chemical sites and whatnot. It would be great if we could have some simple method of constantly detecting the compositions of gases in here. And so having an unmanned aerial vehicle, much like a plane flying over these areas, could prove advantageous. Also, mobile surveillance in large areas can be an issue. If the cameras are just fixed, it may be simple to find ways around them in tight spaces and whatnot. With a mobile camera, not only is it just the camera rotating, rather it's moving around. It can get into crevices and check things. And this also comes with the promises of uses by the government. So in areas too dangerous for human life, things like minefields, or just areas too small for us to physically be there, this could prove quite an asset.
So actually, we saw some videos of us attempting autonomous flight, and we never quite completed a good flight. So last night, despite having completed the competition, we decided that we wanted to try it one more time because we were oh so close to getting it right. And actually, I did not touch the controller, not even a little bit. Hands off the controller.
Wait, Christian, keep filming. I did not touch the controller. Resolution's not being controlled at all. But the altitude, I mean, it was beautiful. And we had it hovered for 2 seconds. That was.
So yeah. Any questions?
So I have a question. And I don't know if you can go back to your slides, but you guys, when you started to position your additional equipment, did you think about setting up a mass, how you're going to maintain the balance? Because you did have a problem with that when you were outside, inside. And so how did you approach that problem?
So,
I was going to point one particular instrument that we were concerned about in terms of not being level was the ultrasonic rangefinder. So in the initial mount that you saw, the one that used the screws over on the sides, we had built a sort of swiveling gimbal sort of setup that would usually stay constant pointing at the ground as the quadcopter would move forward, because we noticed that it tended to tilt as it would move forward. And with that, we were able to kind of get much better height read for that mount.
yeah. Also, in terms of like the center of gravity, like where we position everything. So the DJI Phantom is quite amazing in that, like, if you put a weight on the corner of it, it will stabilize itself without you having to do anything. So there are videos online of people putting weights, like insane weights on like the left side of the copter, and it like just fixes itself quite easily. So from the very beginning, we could place pretty much anything anywhere and not really worry about it.
That said, we never had anything straying on any of the edges. We kept most of our instruments right at the center and built it so that one half of the bottom of the Phantom would be taken up by the GoPro, and then the other half from the mount that you saw.
Also, the drifting wasn't caused by mass distribution. It was just caused by the fact that it was indoors as opposed to outdoors. The first video was on clean core, and it was very, very stable. We were actually astounded. But then indoors, like you saw, the drifting, because it was indoors, the drifting was a problem.
Does that seem logical?
I guess because on the Phantom, there's no, it has GPS enabling, so that's only available outdoors as opposed to indoors where we just have the remote control. So if you nudge the joystick, it keeps it flying in that direction as opposed to just nudging and stopping.
You actually witnessed that in our video of autonomous indoor flight in Lobby 7. Ideally, it would have just gone up and down,
Yeah.
but there was some swaying going out to the sides there, which we, at some point, must be able to correct.
And it's also surprising because like GPS has like maybe 2, maybe 1 meter if you're lucky error. So I was surprised that outside it, but it's a huge difference. Even with wind, it just stays there. It's it's pretty amazing.
Yes?
Can you talk a little more about your thought process in first going with the plan B and then when you decided to pull the trigger?
So there became a point a couple of days before the competition when we realized that we really didn't have enough time to perfect the whole autonomization process, if that's even a word. And so we realized that the safest option would be to get the most effective indoor flight going. And because every time we flew, we would have Moti practicing it with a bit more emphasis so that he'd be ready, we thought it would just be the best fit, rather than having something that wouldn't quite work at all autonomously.
Yeah, but we also didn't go like willy-nilly into autonomous. The way we designed our process was, were we to fail at making it autonomous, we could still use the sensors, and we absolutely used them. Moti told you earlier that we used the ultrasonic rangefinder to go through the hoops. He was a position above the course, and it was quite hard for him to see how high it was. The readings were coming in very quickly, and David was reading out off to him. He didn't have to worry about height at all. For the second challenge, although we failed to pop the balloon, we popped it afterwards like on purpose, like near the quadcopter, and from the computer we immediately got chemical readings and it was accurate. So we designed it in such a way that if we did fail at not all our work would just go to waste, like we could still implement what we had worked on so hard, as our transmitters are.
And I also believe we put a lot of time into our thought process. We spent like 2 weeks thinking about how we were going to implement everything and spent 1 week trying to implement everything. And actually, learning how to pilot the quadcopter is a bit of a challenge because I thought it was just going to be like a simple toy to pilot.